Now that I've given an overview of concurrency as a concept, let's talk about how concurrent programs are developed in Java. And there's a couple of different parts to this because there's a lot of concurrency stuff that's been in Java over a long period of time. So we're going to start by describing how Java supports concurrent programming concepts. And we'll begin with a discussion of so-called thread objects, which is the most obvious starting point because we need something to run things computationally. And here's just a little snippet of some of the interesting methods in Thread. Thread has quite a number of methods, but these are some of the ones that are most useful to know about. Now, it's turned out within the last year or so, ironically around the same time that ChatGPT started coming out, Java threads underwent a major change as part of something called Project Loom and Java 19. I think we're on Java 20 now, but this whole real fun started with Java 19 when you could really get access to the features we're about to talk about. So what are Java threads? Well, the first thing to remember is that a Java thread is an object, just like lots of other things in Java are objects. Not everything in Java is an object. There's a newer feature called a record, which is not an object. But historically, everything in Java was more or less an object. Because it's an object, it therefore contains methods and a slew of internal fields. And so here, again, are some of the methods that are important. We'll talk about things like the run method and the start method and so on, and the join method. And then there's a whole bunch of fields that you don't normally see unless you poke around in the source code, which you're welcome to take a look at or read this link here. And what you'll see here is there's a bunch of things like each thread has a name, it has a priority, it has various properties. Is it a daemon thread? What is it going to use to run the computation when it's executing? How big is the stack? What's the thread ID? Et cetera, et cetera, et cetera. So there's a bunch of things that are part of its state. Historically, because of this state, each Java thread had its own unique instance of its name, its priority, its ID, its runtime stack, its thread local storage, various registers and instruction pointers it has, and so on. Now, when we talk a little later, we'll see there's also a bunch of shared state that is shared between things when you have threads. But there's a lot of stuff that's internal and unique to a thread. So this is basically data or information that resides with each thread. Traditional Java threads, which have been around since the beginning of Java back in the mid-90s, early to mid-90s, are now called platform threads. And we'll talk a bit more about platform threads later. Platform threads are typically mapped one-to-one between the abstraction you see at the user programming level, the thread object, and the underlying resource or resources that are allocated by the operating system kernel. So there's typically a one-to-one mapping between a user thread and an operating system kernel thread. That's what's called a platform thread. And it's a little bit beyond the scope of this class to go into detail about the pros and cons of platform threads, but essentially this is the way things used to work. That was your only choice up to recently, about a year ago or so, with Java 19. The new virtual thread mechanisms, which are now part of modern Java, or what I like to call very modern Java, are lightweight concurrency objects. And so rather than having a one-to-one mapping between object in user space and resource in the kernel, there's a many-to-one or many-to-many, M-to-N mapping between the threads that are the virtual threads and the actual computations that run under the hood, which are called carrier threads, which are basically platform threads. And one of the things you can do with virtual threads is you can have literally hundreds of thousands, if not millions of them, and the system doesn't come crawling to a halt because it has too many resources allocated. Whereas with platform threads, if you had more than several thousand, you could start having things crawl to a screeching halt because it just was taking up too many resources, especially memory in the operating system. These topics are covered in great detail in a sibling course. This is the course I teach in the spring. However, if you would like to learn more about this, because this is an absolutely fascinating topic, take a look at this playlist. This is my list of structured concurrency with very modern Java. Should be very modern Java because this is super up to date. And it talks about platform threads and virtual threads and shows some cool examples and walks through lots of different ways of using it. There's a whole slew of other concurrency mechanisms called structured concurrency that's now part of very modern Java, which we also will not cover in this class, but I'll cover that in the spring. Threads can also be in various states. And the traditional Java threads or the platform threads are in one of a number of states at any given time. So when you create a thread, when you say new thread or new my thread, you make a thread and it's in the new state. When you call the start method, it transitions to the runnable state, which means it's capable of being run. When the scheduler decides it can actually start to run, it goes into the running state. While a thread is running, it can do various things. For example, it can try to access a guarded resource, which will cause it to be blocked. It may end up going and waiting on something, like it waiting to be notified, so it goes into the waiting state. It can also do a timed operation, like a timed sleep or a timed wait or a timed join. It goes into the timed waiting state. And then based on various factors, for example, if it gets a resource it's waiting on, or it's notified, or its timeout elapses, it transitions back to being runnable again. Remember, runnable doesn't mean it's running, it just means it's capable of running. And then the scheduler at some point will make it run. And then at some point along the way, the run method will return, either because it fell off the end or an exception that was not caught occurs, in which case the thread is terminated. So those are some of the states of classic Java threads, platform threads. Modern Java virtual threads can also be in a bunch of different states. And a lot of what's going on here has to do with whether or not they're running on the core or a platform thread, carrier thread as it's called, or whether they're parked off to the side waiting their chance to run again. You can see some of the states are the same. So there's a new state, a started state, a running state, a terminated state, and so on. But there's also a bunch of other states that occur in the implementation underneath the hood. So you don't really have to know all these implementation details, just kind of giving you a deeper view of what's happening under the hood. We're not going to talk a lot more about the details of Java threads in this course. Java virtual threads are multiplexed atop a pool of carrier threads, which are basically platform threads on steroids with a few other bells and whistles that they've added to make them capable of being swapped back and forth rapidly, from parked to unparked rapidly, so you can basically keep the cores as busy as possible without requiring a full-blown one-to-one mapping between the thread abstraction in user space and the kernel thread abstractions running down in the operating system. And so what will happen here is when you have a virtual thread, if you do an operation that would cause it to block, like reading from the user input, or reading from a socket, or writing something, anything that will take a while to block, rather than causing that thread to entirely stop, which is what happens with platform threads, instead it will simply park that thread off to the side on a queue, and then find another virtual thread that is waiting to run and let it start to run, or runnable, waiting for one that's runnable. And so by doing this, you can have a small number of carrier threads, which we see at the very top, and then you have a bunch of virtual threads, and you can see that they're multiplexed over top of the carrier thread. So only one of the virtual threads is running on a carrier thread at a time, but it's able to move very quickly back and forth, so the context switching overhead is much less. So that's one of the great things about being able to use virtual threads. It reduces the amount of overhead, and therefore you can have lots and lots of these things, and everything scales up quite nicely. So that's the end of this part one of how concurrent programs are developed in Java.